Select the major product of the following reaction. So you want to take a look at what we're starting with, and we're going to go sequentially through these steps. So we see that we are initially starting with a ketone. And what we're treating this ketone with is LDA, and LDA is lithium diisopropyl amide. And what this is a really strong base. So let's draw the structure of that base here. And so it's going to react with the most acidic hydrogen in this ketone, which is going to be these alpha hydrogens. So we have a ketone that has alpha hydrogens on only one side, so we don't have to decide whether we're forming a kinetic or a thermodynamic enolate, which is one reason why we're not indicating the temperature here. So we can go ahead and show how this base, this diisopropylamide, and the lithium is just a counterion. So I want to see how this is going to form the enolate. So it's going to grab any one of these alpha protons, and we can put the electrons here on this carbon. And you can draw the resonance structure as well that would delocalize that electron pair onto the oxygen. I'm going to keep them onto the carbon so we can see where this molecule is nucleophilic. So what this step does, because this LDA is a really strong base, it's going to completely convert this ketone into the enolate. So complete conversion to the enolate. And so that's important because if we had some of the ketone around, the enolate could react with the ketone in an aldol reaction. So clearly we don't want this reacting with itself. We want it to react with this second carbonyl component that we're adding in. So we're adding in an ester. So this is just, it doesn't have a fancy name, it's just a crossed condensation reaction. Okay, so an enolate here is a nucleophile, so it can attack the electrophilic carbon of the ester. So I'm going to go ahead and draw that ester. I'll draw it in a different color so we can keep track of what piece of our product is coming from which one of these starting materials. And we are going to use the same sort of shortcut mechanism we've used in the last few examples. So we know that this enolate will attack the carbonyl because that carbonyl is electrophilic. Being that this is an ester, this would push electrons up onto the oxygen, giving you a tetrahedral addition intermediate. The electrons would then come back down and kick off the leaving group. So we are going to shortcut that by saying the electrons come up, they come on back down, and they kick off the leaving group. And so we will note that this is a shortcut mechanism. So even though it's a shortcut, though, it gives us a really good and fast way to get to the product. So we can draw the product of these two coming together. So we have the ketone, and so here's the CH2 of the ketone that attacked. And if we had any more of the chain, I would angle it down this way. We don't, so I'm not going to. We've got the benzene ring. Okay, and from this alpha carbon to the carbonyl, that is our new bond. So we will highlight that new bond here. And then we're going to show what is left of the ester that we attacked. So it lost that OCH3 as a leaving group. The electrons came up and back down again, so we still have a carbonyl. And then we have the rest of the chain, which is just this one methyl group in this case. Okay, and we also kicked off the methoxide. So what happens in this last step is a reprotonation, because this methoxide is actually going to remove one of these two protons to give you the anion. It's acid-base chemistry that you can't stop. So you'll have the anion there, and then you have to put the proton back on. So that's why we acidify it in the last step. But in terms of getting to the product, we've got enough here. We've got the product. We just got to pick it out of what we see down here. And we ended up with this diketone, and that is the same as B. And I'm just going to go ahead and color in the section so we can see that. It should be obvious that this is just kind of like flipped around from how we drew it there. We should be able to see the same connectivity. So these are the atoms that came from that attacking enolate. And then what's left of the ester is just the carbonyl and that methyl group. And of course, this here is your new bond.